There are moments in the quiet vigil of science when the universe doesn't just whisper its secrets, it roars. When a single photon, stretched across billions of years, pierces the veil of cosmic time and lands like a thunderclap on a sensor a million miles from Earth. Moments that don't merely add footnotes to textbooks, but demand we rewrite the prologue to existence itself. The James Webb Space Telescope, perched at the edge of our solar system, has become that unrelenting herald. In the summer of 2025, as its golden mirror captured light from the farthest reaches yet probed, it unveiled not one, but a cascade of revelations, galaxies blooming in the infant universe, not as fragile seedlings, but as colossal titans, their arms spiraling with the grace of ancient spirals, their hearts pulsing with stars forged in efficiencies that mock our equations. These aren't anomalies. They're an indictment. According to preliminary findings from NASA's JWST Advanced Deep Extragalactic Survey, or JADES, objects like MUMSI 14, existing a mere 280 million years after the Big Bang, shine with the chemical signatures of maturity, nitrogen and carbon woven into their spectra as if the cosmos had been brewing heavy elements for eons longer than our models allow. This isn't astronomy adjusting its lens. This is physics staring into the abyss of its own making, wondering if the Big Bang's echo was ever truly the beginning. Imagine the scene unfolding in the control rooms at NASA's Goddard Space Flight Center, screens flickering under the hum of servers, straining against terabytes of infrared data. It's late 2024, and the first deep field images from Webb's NIRCam instrument flood in, a tapestry of crimson and gold against the void. Astronomers, bleary-eyed from nights blurred into days, lean closer. They expect the faint glows of proto-galaxies, diffuse clouds of hydrogen collapsing under gravity's patient pull, birthing the first stars in fits and starts, as dictated by the Lambda CDM model, our cornerstone of cosmology. This model, refined over decades from cosmic microwave background whispers detected by satellites like Planck, paints a universe born in a scalding plasma 13.8 billion years ago, expanding under the twin forces of cold dark matter's gravitational scaffolding and dark energy's relentless push. Structure emerges hierarchically. Tiny dark matter halos seed the first stars. Population 3 behemoths, hundreds of times the sun's mass, their fusion igniting the reionization era around 400 million years post-bang. Galaxies coalesce slowly, mergers sculpting irregular blobs into disks over billions of years. Star formation rates peak modestly, converting perhaps 10 to 20% of gas into luminous matter, the rest locked in inefficient cycles of cooling and feedback. But Webb's gaze, piercing deeper than Hubble's ultraviolet limits, reveals a different genesis. In the JD's fields, ultra-deep exposures of tiny sky patches near the constellation Ursa Major, the telescope isolates a pinpoint of light, cataloged as JD's GSZ 14-0. Spectroscopy with Webb's NIR spec instrument confirms its redshift at Z equals 14.32. Light emitted when the universe was just 290 million years old, stretched into the infrared by expansion's merciless tide. This galaxy isn't a tentative spark, it's a blaze. Its spectrum brims with Lyman alpha emission, hydrogen's ultraviolet fingerprint redshifted to near-infrared, indicating not just stars, but a vigorous outpouring of ionizing radiation that should have been smothered by the era's neutral hydrogen fog. Preliminary analysis reported in Nature Astronomy in early 2025 estimates its stellar mass at over 10 to the 8 solar masses, hundreds of times what Lambda CDM simulations predict for such tender ages. It's like finding a fully assembled city in the ruins of a Stone Age camp, muses Stefano Carniani of the Scuola Normale Superiore in Pisa, a lead on the JADES team. The emotional weight lands heavily. If one such outlier exists, it strains the model. If dozens do, as Webb surveys suggest, the strain becomes a fracture. The data pours in relentlessly. By mid-2025, teams from the University of Missouri sift through NIRCam images, applying dropout techniques, filtering for objects vanishing in shorter wavelengths, a hallmark of high redshift. and spectral energy distribution fitting to unmask 300 unusually bright candidates. Published in the Astrophysical Journal, their work flags these as potential galaxies from 200 to 400 million years post-bang, their luminosities defying luminosity functions extrapolated from Hubble's ultra-deep field. These aren't faint dwarfs, they're hyperluminous, some rivaling the Milky Way's output crammed into volumes a fraction of Andromeda's. One, dubbed a blue monster in informal team chats, clocks a specific star formation rate, stars born per unit mass, 5 times higher than local benchmarks, converting gas to glow with near total efficiency. Dust, that cosmic veil which tempers modern galaxies' fury, is all but absent. Mid-infrared spectra from Webb's MIRI instrument show scant polycyclic aromatic hydrocarbons, the molecular fingerprints of stellar nurseries tempered by metals. It's as if these primordial forges operated without brakes, gravity funneling pristine gas into stellar infernos, unhindered by feedback loops that should quench such excess. Zoom in on Zhulong, a serendipitous find announced by Swinburne University astronomers in April 2025. Caught in a parallel JWST observation of a lensed cluster, this spiral galaxy candidate gleams at redshift Z equals 5.2, 1.1 billion years after the Big Bang, still achingly young. But its structure haunts, a central bulge of aged stars, a vast disk laced with well-defined arms, echoing the Milky Way's form a billion years premature. Gravitational lensing from foreground clusters amplifies its light, but even unlensed, its mass exceeds 10 to the 11th solar masses, implying rapid coalescence. Simulations under lambda CDM, like those from the illustrious TNG project, allocate eons for such grandeur. Mergers of dwarf halos, angular momentum conservation spinning disks over gigayears. Yet here it spirals, as if the universe conspired to sculpt elegance from chaos in a cosmic sprint. It's a twin we weren't ready to meet, reflects Carl Glazebrook, the lead investigator, his voice carrying the quiet awe of discovery laced with unease. The emotional undercurrent swells. These aren't relics of a tidy origin story. They're harbingers of a universe that bootstrapped itself, defying the slow simmer of our predictions. As the anomalies mount, the scientific community stirs, not with outright panic, but a deepening disquiet that echoes through virtual seminars and archive preprints. In November 2025, the CANX survey unveils CANX LRDZ 8.6, a little red dot galaxy at Z equals 8.6, 570 million years post-bang. Its compact core hides not a stellar cluster, but a supermassive black hole gorging on gas, accreting at rates that outpace Eddington limits by factors of 10. Webb's NR-spec spectra capture broad emission lines, nitrogen-3 and carbon-4, indicating outflows that should sterilize star formation. Yet the galaxy thrives, its ultraviolet luminosity suggesting a star formation rate of 100 solar masses per year, dwarfing the Milky Way's sedate one. Roberta Tripodi of the University of Ljubljana, lead author on the discovery, shares in a European Space Agency release, "This black hole grows faster than we thought possible in such a small host. It's remarkable, but it challenges how we link black hole seeds to galaxy cores. These little red dots, dozens now cataloged, pulse with active galactic nuclei, their infrared excess hinting at obscured growth. If black holes seeded galaxies rather than vice versa, as some models now propose, it flips the hierarchy. Gravity's dark anchors, pulling light into being, not the other way around. The urgency builds in the data's relentless flow. Webb's Uncover program, targeting the galaxy cluster Able 2744's natural lens, exposes 83 young galaxies at Z equals 7 to 9, their doubly ionized oxygen lines screaming vigorous starbursts. 20 received deeper NIR spec scrutiny, revealing escape fractions of ionizing photons around 25%. Enough, if widespread, to drive reionization single-handedly. Brian Wold of NASA's Goddard, co-author on the findings, notes in a June 2025 press release, "These tiny galaxies pack a punch. Their ultraviolet output could explain the fog's sudden lift, but only if they formed en masse earlier than our timelines allow." Emotional peaks crest here, in the tension between awe and apprehension. Picture the first authors poring over spectra at dawn, the room thick with the scent of cooling coffee, as lines align not with expectation, but with impossibility. It's the thrill of the hunt yielding a quarry that devours the hunter's map. Yet amid this bounty, a surprising reveal emerges, one that twists the knife of doubt deeper. In October 2025, University of Arizona researchers dissect JADES GS 14-0 further beyond its record distance. Mid-infrared data from MIRI uncovers not just brightness, but complexity. Oxygen abundances rivaling those in galaxies twice its age, forged in supernovae cycles that demand prior stellar generations. We expected hydrogen and helium dominance, says the team's lead, but this galaxy brews metals like it's midlife, not newborn. This isn't mere overluminosity, it's evolutionary precocity. Lambda CDM accommodates bright outliers via bursty star formation, stochastic spikes where gas clouds collapse in unison, spiking rates by factors of 10 for brief epochs. But sustained efficiency? That invokes top-heavy initial mass functions, where massive stars dominate, their short lives seeding metals rapidly. Or perhaps population 3 stars, pristine and colossal, ignited clusters that outshone simulations. The reveal lands with a jolt. If metals abound so early, the cosmic dawn wasn't a spark, but a bonfire, reionizing not gradually but in a flash that scatters our timeline like embers. Deeper still, Webb confronts the expansion paradox head-on. The Hubble constant, that measure of cosmic stretch, has long chafed under tension. Local measurements via Cepheids yielding 73 kilometers per second per megaparsec, while cosmic microwave background echoes whisper 67. Webb's standard candles, type Ia supernovae lensed across clusters, nudge the debate, but high redshift probes like these galaxies test the fabric. At zeta equals 14.44 for MOMZ14, light crosses the Hubble sphere, where recession exceeds light speed, yet arrives intact. Relativity holds, the sphere expands, hauling horizons forward, but the maturity of these beacons implies structure predating the microwave background's 380,000-year freeze-out. We're seeing fossils of a structured infancy, posits Eli Visbal of the University of Toledo, whose November 2025 study in Live Science suggests population 3 stars in LAP1b, lensed by MAC SJ0416. Gravitational amplification magnifies their glow 100-fold, but the signal's purity, undiluted by metals, hints at first-light clusters, their formation hinging on supersonic gas flows in dark matter-free halos. The emotional core of this saga pulses in the human element. Scientists, guardians of certainty, now stewards of uncertainty. At conferences like the American Astronomical Society's January 2025 gathering, panels dissect the impossible early galaxy problem. Rachel Bezenson of the University of Pittsburgh, uncover principal investigator, fields questions on tweaks to dark matter's clumpiness, a steeper primordial power spectrum perhaps, seeding denser halos. But qualifiers abound, based on preliminary spectra, if confirmed by ALMA follow-up. The tone shifts from urgent debate to reflective pause, the weight of 13.8 billion years pressing on shoulders trained for precision. One cosmologist, speaking off record, likens it to Copernicus gazing at stars that refuse geocentric orbits. Not a shatter, but a slow unraveling, forcing eyes toward horizons unseen. Climax arrives in synthesis, as 2025's deluge coalesces into a mosaic of menace to the model. Over 300 bright dropouts from Missouri survey, 83 reionization drivers from Uncover, 5 galaxy pileups at Z equals 8 from a September Live Science report, each a thread pulling at Lambda CDM's weave. Star formation excesses, probed via gamma-ray bursts in an October R-Shift paper, suggest bursts at Z greater than 10 could explain luminosity spikes, but demand Einstein probe detections to confirm. Black holes in little red dots, overmassive by factors of 10 to the 6 solar masses, imply direct collapse seeds bypassing stellar remnants. In spirals like Zhulong, they evoke modified Newtonian dynamics whispers, though most cling to astrophysical salvations. Bursty histories, reduced dust, efficient accretion. Yet the pattern endures, a universe not dawdling in infancy but sprinting toward adolescence, structures emerging with a velocity that causality strains to contain. If even 10% of candidates hold, simulations falter. The halo mass function, tuned to Hubble's SC equals 7 limits, buckles under JWST's infrared scrutiny. In the resolution's quiet gravity, we confront not defeat, but invitation. Webb hasn't slain the Big Bang. Its inflation epoch, nucleosynthesis yields, CMB anisotropies remain unassailed. But it demands evolution. Hybrid models blending tired light with expansion, or cyclic cosmology stretching time to 26.7 billion years, as a 2023 Science Daily outlier posits. Preliminary 2025 data from ESA's Webb releases hints at Lyman alpha escapes in JD's GSZ 13.1 at C equals 13.05, fog-cleaving photons from 330 million years post-Bang, suggesting patchy reionization driven by these precocious beacons. The emotional arc crests in reflection, awe at a cosmos more fecund, more furious than fathomed, humility before data that humbles theory. It's a call to rebuild, not from rubble, but from richer foundations, merging JWST's gaze with ALMA's millimeter eyes, Euclid's wide surveys, probing the dark matter's role in this accelerated assembly. As the telescope's fourth year beckons, with Cycle 4 proposals vying for mirror time, the question lingers like starlight on the retina. Did the universe truly ignite in singularity's flash? Or does Webb illuminate a prelude, an eternal churn where Big Bangs are but phases in infinity's breath? These discoveries, raw and revelatory, urge us onward, not to cling to certainties but to chase the next horizon, where physics might mend what it once mistook for whole. What do you see in this fractured dawn? Crisis or catalyst? Share your thoughts below, subscribe for the revelations yet to unfold, and let's witness the rebuild together. Information updated.